Hello physics students. In this video we're going to be testing the law of conservation of energy again. Now at this point you should have once again printed out the pages 3 and 4 of the lab sheets in the Google Stream, the PDF file. Again, pages 1 and 2 are instructions. You're welcome to print those out if you want to, but you don't have to. Okay, so this is what we're going to be studying in this experiment. We're going to have a car up like this, and then what I'm going to do is I'm going to tap this spring and this pin and release the spring so that the car shoots across the track. Now you need to decide what kinds of energy or energies the car has before I release it, and what kind of energy or energies it has after I release it. So, in other words, when the car is there waiting to be released, what kind of energy or energies does it have? And then when I tap the pin and release the spring, what kinds of energy or energies did it have as it rolled along the track? I'm not going to tell you. You're going to have to figure that out on your own. And then what we're going to see is that energy of the system before should, in theory, equal the energy in the system after. To prove this, we're going to need a whole bunch of data. So what I'm going to do is reconfigure the camera and show you how I collect the data to prove that, or to demonstrate that energy is conserved in the experiment. Okay, so the first step of the lab, number 1, says to mass the car. We're obviously going to use an electronic balance. So I'll turn this on, put the car on the balance, and I get 255 grams here. But of course, I'm going to convert to kilograms before I put that on the data table, which would be, for me, 0.255 kgs. So I put that here. You may not be able to see that on the screen, but again, you're not writing that down. You're going to go into the Google document or the document in the Google Stream and get the mass of the car assigned to you for this experiment. Okay, let me get the balance out of the way. The next thing in step 2, not only does the mass affect the energy of the system, but also the characteristics of this spring in here. Specifically, what we want to do is determine the spring constant of this spring. So what we're going to have to do is we're going to have to see how much it displaces for a given load. So step 2 says that what you want to do is place an index card on the top of this car and measure the distance from the top of the card to the table with your ruler. So for me, I get about 20.90 centimeters above the tabletop. So that's what I get measuring that index card. And so I'm going to convert that to meters and put it in my data table. 0.209 is 20.9 converted. So that went right here in the data table. Again, you're going to look in the Google Stream for your own data. Next, what I'm going to do is I'm going to balance a 500 gram mass on that spring while holding this little pin down to prevent the plunger from getting stuck on the little pin. So what I do is I kind of go like this and I shake it around a little bit till it finds its equilibrium. And now we see the spring displaced. It went down. I'm going to measure the new spring height, which for me I get as 18.90. 18.90. So again, I convert that to 0.189 meters. So that goes into the second box or the third box over here. Again, you're getting your data from the Google Stream. And so that's basically the data that I needed from the spring. Okay, so let me configure the camera and we'll move on with the calculations. So these are the numbers that I've recorded so far in this experiment. Again, you're not recording these actual numbers because you're going to go into the document in the Google Stream to get your own data. Now, we're up to 2E in the procedure. 2E says calculate the spring displacement, and you do that somehow from these numbers. If I call this X initial and this X final, what will be the spring displacement in terms of those two? You're going to make a formula. Then you're going to plug in the numbers here, and then you'll get your final answer here of the spring displacement. Don't forget to label the value with a unit also. So there are your 3 steps. So that's spring displacement, again, from these 2 numbers here. Then we're on to part number 3, or step number 3, which says calculate the spring constant of the spring. Now remember, the spring constant, the symbol for that is K. Let me move this up a little. Okay, so this is what we're looking for. We're looking for the spring constant K. Now, here are some things that we've determined already in this lab. We determined the spring displacement X, so that's in 2E. And then you also know something else. The thing that caused that spring to deform the way it did was this block of metal, which I placed on top of the car's plunger, pushing it down. Now that turned out to be 500 grams. But that's not what we use. We don't use the grams. We've got to somehow, through a couple steps, convert that to a force, which is measured in newtons. So that's for you to figure out. How do you get this to be the newtons that pushed the spring down? What force was it when I stacked this on top and it pushed it down? What force do we call that? Calculate that force for 500 grams. Use that force, that X, to calculate K by looking for a formula on the reference table. Something to do with springs. So again, I'll leave that for you, determining the spring constant. That's what you've got to figure out. Okay, so that's number 3. Hopefully over here you have K equals, and then don't forget the units that belong there also. Okay, so that was step number 3. Now we go to step number 4. You will push the spring in all the way. Place the car on the track so the spring plunger, spring plunger is against an immovable surface. Then tap the release pin so the car moves on the track. For this motion, write an equation that states energy is conserved in this case. Hint, an example of an energy equation is PEG equals W, but this does not work for this experiment. Write the correct equation for the car pushed out by the spring and then rolling along the table. So let me show you the motion again, because basically you have to generate a formula. Right here, you're going to write out a formula. Again, it's not this, PEG equals W. Not this, but it's going to look something like that, some kind of energy conservation formula. So let me show you a replay of what we saw earlier. This is the car before release, and this is the car after the release. So think about, from what you just saw, what kind of energy it had before, what kind of energy it had after. Write that formula right there. Okay, so let's go on to number 5. It says, determine the spring displacement when the plunger is pushed all the way in. this will not be the same as the distance in procedure step 2E, which was right here. Now, how do we determine that? We're going to be pushing this spring all the way in for this experiment. So we've got to find the spring displacement for this spring pushed all the way in. So what I need is my ruler again, which I seem to have misplaced. Let's see. Okay, under the track. Ah, there it is. Found its way under the track. Okay, so here we are. The way we're going to do this is the same way, but what we're going to do now is figure out how far in front of the plunger how far the plunger extends outward. What I'm measuring is about 5.1 centimeters. And then when I push it all the way in, I'm measuring approximately 0.7 centimeters. So from 5.1 to 0.7, what I need to do is find that spring displacement by saying it was 5.1 centimeters minus 0.7. That's how much it changed by when it was pushed in and when it pops back out. That gives me 4.4 centimeters. So maybe what I'll do is this time everyone will have the same spring displacement here. Okay, so there is my spring displacement. You could go ahead and write that down also in your lab. Okay, so now we're on to step 6. See, here we got 5. Here, up here, we have 6. So what is 6 asking us to do? Well, let's go to our procedure. Plug the spring displacement value from step 5 and all other appropriate data into your equation and solve for the theoretical velocity of the car after the spring releases. So remember, we have this formula here, not this one, right? You made your own. So you're going to write the correct formula, some kind of energy before equals some kind of energy after. And then you're going to plug in all the appropriate data into that formula. And when you're all done with your algebra, in the end, you're going to have the velocity or speed of the car with some appropriate unit there. So that's what you do in this step. Go ahead and do that now. Okay, so the next several steps are basically setting the track up and running the experiment. So let me move the camera and we're going to together run this experiment and get the data that we need to test whether or not this velocity is accurate, whether or not the experiment produces the same velocity. Okay, so instead of reading the procedure, I'm just going to walk you through the experiment and explain what I'm doing because I think it'll make more sense that way and it'll be more efficient. So at this point, you have a velocity or speed, I should say, predicted by the law of conservation of energy. So what we want to do now is test that law to see if we get the same velocity when the car is released, the spring is released and the car rolls along this track. So in order to evaluate whether that's true, the velocity will be equal to the theoretical velocity, we first have to level the track. So I can do that with just putting the car on the track and giving it a little nudge in both directions and making sure that the motion is the same in both directions. And you see it kind of rolls to the, well, your left, pretty easily, but to the right it doesn't roll. In fact, it tends to reverse directions. That means this end of the track is too high. So probably left over from my Newton's law experiment where I tilted the track to overcome friction. So I want to turn this screw to bring this end down until the track appears to be level. So I go like this and it still tends to look like it wants to favor this direction. You see how it goes this way and then it comes back. So I want it down a little bit more. Let's see now. All right, rolls this way, rolls that way. Well, now I went a little too far. That looks pretty good, okay? So now I have the track leveled, and what I'm going to do is I'm going to let this go and shoot across the track. And now I need to calculate the velocity somehow. So remember, there's a formula for velocity, or speed, I should say, and it includes distance and time. It's on the reference table. I'm not going to tell you what it is. You need to find it. So we're going to measure the time, we could, in theory, use a stopwatch. It would be okay in this experiment, but stopwatches, again, because it's our fingers, are notoriously inaccurate. So we're going to use the photo gate again. The problem is that when this car rolls past the photo gate, it doesn't go through the photo gate. Remember, the photo gate was, the way it operated was there was an invisible beam here, an infrared beam you can't see with your eyes. And in the pendulum lab, what happened was that the pendulum here, the mass, swung through the photo gate and interrupted the beam. And that's how I got my measurement. So again, it swung through like this, right? Just like that, and it was giving me a measurement. The problem in this experiment is that when the car goes by the photo gate, look what happens. None of it passes through the photo gate. So this car would pass the photo gate, and the photo gate would never measure anything. I solve that with a little trick. What I do is I put a little plastic strip on this car, and now look what happens. The plastic strip passes through the photo gate. Okay, so that's what's going to stimulate or trip the photo gate to record the time. So that means before, in the last lab, I recorded the diameter of the mass as it swung through the photo gate. But now, it's not the mass that's swinging through, it's the plastic strip. So what I need to do is measure that distance of the plastic strip that's stimulating the photo gate. So, I'll get my ruler out. And I get about 1.69 centimeters. So there's no space for that in the data table, but we do use it in a calculator, in the calculation. So what I'll just do is write it on the scrap, or write on my lab sheet here. So 1.69 centimeters, which is 0.0169 meters. Okay, so I'm going to keep that distance for later. But again, you're going to look in the Google Stream for your own plastic strip length. It'll be listed there. So now I'm going to affix this to the car. And I'm going to do my best to make it stick out from the car at a 90-degree angle to the car. So I just, I don't have a protractor, wouldn't really work that conveniently, so I'm just going to kind of eyeball like this. Okay, oops, wrong way. It's got to go this way. All right, ready to go? So, sometimes this doesn't like that. Now I'm going to tap this little release pin, releasing the spring. We'll see this shoot across and go into the photo gate, and we'll get a time registered on the screen here. So here we go. Okay, so there it is. You may be able to see that on your screen. Once again, you're not copying this down. I'm going to copy it down for myself, but you're going to get your own data assigned in the Google Stream. So here we are. We have a velocity already calculated according to the theory. According to energy conservation, there was a prediction what the velocity should be. Now what we're going to do is see what the experiment generated for velocity and compare it. What do we have to allow us to calculate this velocity? Well, at this point we have a distance that came from the plastic strip, the thing that stimulated the photo gate. We have a time that came from the photo gate. Again, you're going to get these two pieces of information in the Google stream. So you're going to start with a formula as always. You're going to make a substitution, and then you're going to get an answer here with the right number of units. So that's the calculation you make with these two pieces of data. Again, you've got to find the formula and you've got to calculate. And then in step 13, you're just going to do a percent error between these two velocities. Now, what I'm going to do is make up a number, a series of numbers. Let's suppose you calculated this to be 2.1, and the units I'll leave off here because you got to figure those out yourself. And then over here, you got 2.2. Okay, so you basically are showing the car going faster than what was predicted according to the law of conservation of energy. So now what we do is we move on to the questions. Okay, so we're all the way through 13 and we're on to 14. Judging from the theoretical velocity and the experimental velocity, was energy gained or lost in this experiment? Explain how you know. So you look at this number, you see that this one was bigger. So according to our experiment, was there energy gained or lost in the system? So you cannot just say, O is gained or O is lost and stop. You have to explain how you know from these two numbers alone. And then, so that goes into this space here. You're writing out with sentences, right here, okay? And then 15 says, give two reasons that account for your loss or gain. The reasons must be consistent with your answers to question 14. So what I'm going to do to help you figure this out, I'm going to reconfigure the camera so you could see the original setup so I could talk about some possible sources of error. Okay, so here's my original setup. And what we're doing at this point is we're trying to write a scientific conclusion explaining away some results of an experiment. This can often be one of the hardest things to do in a lab because basically what you need to do is you have to come up with a valid reason why your results were off. And you can't just say something general like, oh, the results were off because of human error, done, pass in the lab. Or things like, you can't say, results are probably off because I probably made a mistake in my calculations, so that's why they're off. No, an experiment is like an English paper. If there's, for example, when you're turning in an English paper, if there's a spelling mistake on it, you should fix that before you turn your paper in, right? Otherwise, it's not considered correct. Same thing with science labs and experiments. They're considered like a formal final draft of a document. So any calculation error should have been fixed. Any place you rounded incorrectly, so, I rounded incorrectly. No, that should be fixed. We're assuming you did everything right with your numbers, but yet the numbers are still wrong. They're still off. So now you have to think about what could have gone wrong in the setup itself or in the theory, the application of the theory. And it's okay to list something that a person did wrong. You just can't say human error as a general blanket statement and stop the conclusion. So what we're looking for is things that might have not gone wrong in the execution of the experiment. So what I'm going to do is go through the various things that I measured to try and come up with reasons why I could have had a gain or loss. The other thing that I have to do when writing a conclusion is my error that I come up with has to actually explain away the error. For example, let me just suppose for the rest of this video that I observed a gain in energy. You're going to have possibly a gain or loss. That's up to you to decide from your data of the two velocities. But let's suppose my data showed a gain of energy. So one thing I cannot say, oh, maybe there was a magnet over here holding the car back. Because what that would do is it would cause the speed to be, the energy to be less if I was holding the car back. So you're not going to write magnets because there weren't any. But if, let's suppose there was a magnet here. I couldn't use that as a reason why energy was gained, because the magnet here would not cause a gain of energy, it would cause a loss of energy. So keep your eye out for things that could have gone wrong that could have caused your loss or gain. So let me go through what I measured. I measured the mass of the car. Probably not likely to be off because it was an electronic balance. So that's probably not a good thing to list. But then when I put the car on the track, one of the first things I did was I did this leveling business, okay? And I tried to turn this screw until this car was level. This is a valid thing you could list for why energy was not conserved. But you need to be specific. You can't say, oh, you didn't level it properly. You have to come up with which way was it leveled incorrectly for your loss or gain. Was this end too high or was it too low? Said another way, was the car rolling downhill or uphill because of the incorrect leveling? That's valid, okay, as long as you list it consistent with your loss or gain. So that's one thing I did. I leveled the track. Another thing I did was I measured the index card, right? So that was another thing possibly that could be off. And when you're measuring this width, there's a way you have to line the ruler up that if you do it wrong, you could possibly show an inaccurate result. Think about that. All right, if you can't think of it, then think about this. When I put this index card or this plastic strip on the car, my goal was to make it perpendicular to the car. What if it wasn't? What if it was like this? Or what if it was twisted like this, okay? A little bit bent. There's another possible reason for the results to be incorrect. Let's see, what else? Okay, so then at the start of our data collection, I went like that, right? So what could have gone wrong when I hit this like this? Is there a way you could think that I did this that could possibly cause a gain of energy? List that out in detail, the way I might have done this wrong to make it gain energy. Can you think of a reason why doing that might make it lose energy? Okay, you can argue either way with this influence, that it could have caused a gain or loss, but again, you have to be specific, okay? Another possibility is, as this rolls, besides uphill and downhill, there's another influence that causes energy possibly to gain or lose. I'm not going to tell you, but as you're rolling like this, right? What other factor could be present in these wheels that could cause gains or losses? Think about it carefully. Let's see, can I think of anything else? Well, I seem to be out of ideas. So, but I've given you plenty to think about. Again, you only need two things in the setup that could possibly have been wrong. And then you explain in detail how that led to a loss or gain over here. Okay, those two factors. All right, so that's the energy conservation lab for the rolling car. I hope you enjoyed the lab. I'll see you in the next physics video.